Welcome back to What is 5G and how is it measured correctly? Here in part 2 we will introduce you to the technologies that are a part of 5G, which are massive MIMO, beamforming, TDD and FDD. Just like beamforming, massive MIMO is mentioned with 5G in the same breath. But the fact is that both these technologies are completely separate. A modern router, such as may be found in any household these days, can already transmit its signal using MIMO and beamforming. And conversely, 5G doesn't need beamforming or MIMO for it to work. But with 5G, these technologies are being rolled out for the first time with blanket coverage in a mobile network. Multiple input, multiple output, or MIMO for short, describes an antenna that does not consist of just one dipole, but of many. And these dipoles often have different polarization. Even with 2G, the transmitting antennas at least were made up for several cross-polarized transmit and receive elements. This reduced fading effects and enhanced the stability of communications. If a MIMO antenna is also used in a handset, MIMO can also be used to increase transmission capacity. Beamforming has the same physical requirement as MIMO, that is, an antenna that consists of several antenna elements. By feeding the output signal of the various antenna elements with different phases, it is possible to influence the antenna diagram or pattern. Without any mechanical movement, it is possible in this way to sweep the antenna or to change the directional characteristics. Where earlier segment antennas could only cover a fixed 120-degree angle, for example, a beamforming antenna can both cover a fixed 120-degree as well as being able to transmit only in a direct line to the handset. This function is only a question of the control software. Moving parts are no longer required. Beamforming can also increase the antenna gain. Beamforming can be used for both the signaling and for the traffic. Signaling is required in order to set up a connection. It is always transmitted with full output power, as it must be able to detect a new user right up to the edge of the cell. In contrast, the traffic signal contains a conversation and transmits the useful information. Unlike the signaling, the output power of the traffic signal can be reduced depending on the location of the user. Simultaneous beamforming is possible in both spatial direction, that is, vertically and horizontally. Particularly when in tilt mode, the antenna can cover much wider areas with the vertical axis than when it is in fixed 120-degree mode. It is assumed that 3 configurations are used for the most part: both signaling and traffic without beamforming, signaling without beamforming, traffic with beamforming, both signaling and traffic with beamforming. FDD and TDD. In the early years of mobile communication, it was usual for the uplink, the signal from the handset to the base station, to use a different frequency than the downlink. This is shown here by channel 1 and 2. In each radio frame, there are 10 subframes available for the uplink and 10 for the downlink. This technique is called frequency division duplex, or FDD for short. Experience has shown, however, that the uplink is used much less than the downlink. A lot of capacity or the frequency band is therefore wasted. For this reason, more modern systems are making ever-increasing use of time division multiplex technology, TDD for short. Here, the handset and the base station transmit on the same frequency but at different defined times. This allows the number of time slots available in each radio frame for the up and downlink to be set separately, so that they can be adjusted to match the required capacity perfectly. It is thus now possible to make different capacities available for the uplink and the downlink, but with the same number of frequency channels. A so-called special frame is inserted in order to time synchronize the up and downlink. What do these techniques mean for the measuring equipment and how are they measured correctly? We will take a look at that in part 3.